Good evening, Priyank sir. Should we go ahead with the videos of ISHRAE? Hello, Priyank sir, can you hear me? Sir, your voice is not coming, sir.
Hello, can you hear me now?
Yes, sir, it's fine.
Okay, great.
So should we start the webinar with the ISHRAE video, sir?
Yes, please go ahead.
Thank you.
We, the Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRAE helps formalize industry codes and standards. ISHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRAE organizes exhibitions, conferences, panel discussions, and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, Acrex India, to showcase the cutting-edge technology, innovation, and provide a platform for closer interactions amongst the decision makers in the industry. The ISHRAE exhibition is now growing from HVAC and R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry all at one location. Our chapters organize several other popular events like ACRIConf in Delhi, Railcar in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A prestigious quiz competition organized by ISHRAE to catalyze the transformation of the budding engineering professionals. ISHRAE provides a platform to potential employers to select student members for careers in HVAC and R industry at the ISHRAE Job Junction. Young minds are made aware of the need for saving power, clean air, and sustainability. The K-12 initiative of ISHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ISHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection, and energy efficiency and conservation. To enter and explore the universe of the Indian HVACR industry, log on to ISHRAE.in that unfolds a panorama of information. Let us engineer a sustainable future together through ISHRAE.
Thank you very much. Thank you everybody for joining this session. As we know that today we are going to cover the topic of radiant cooling, and for this we have expert speaker Mr. Vikram Murthy, one of the veteran of ISHRAE Society. Yes, this program is organized by Delhi chapter of ISHRAE, supported by ISHRAE India chapter and Premjan Memorial Trust. And of course, this is supported by our gold partner ALP Aeroflex, Standard Refrigeration, annual partners, Standard Refrigeration, Advanced Walls, Fluke, Lord Insulation, and membership partner ALP Aeroflex. Before moving to the agenda, I just want to showcase few slides of our gold partner ALP Aeroflex. Then we will move out. They are into the innovation for insulation solutions. Founded in 1985, you can see a few information portfolio over 10,000 products they have. Key projects what they have done in airport, hospital, IT sector industries, government, educational institution, and prestigious international corporates. These are the product lines of LP Reflex, and for that you can contact here with the numbers or email ID. Thank you. So moving forward, I request Mr. Priyank Shankar Garg, the Secretary and National Event Chair for the Delhi chapter of ISHRAE, to proceed with the introduction of Mr. Vikram Murthy. Thank you. Thank you very much. Over to you, sir. Sir, please unmute yourself.
Thank you, Tapas. Thank you for setting this up. Thank you, Vikram, for being here. And thank you to all the participants. It's great to see 70 persons already with us, and I'm sure they'll come on board. I believe there's another event from Rajasthan chapter still going on. Um, it's my great pleasure and honor to introduce dear friend and the guide, Mr. Vikram Murthy. Um, Mr. Vikram Murthy is a Bachelor of Technologies Electrical Engineering from IIT Kanpur and has spent 45 years in the HVAC industry. If you look at his bio in the flyer, it highlights a few of his past experiences with work in Voltas as a project manager, with a role as a director at Gen Power Private Limited, as well as the executive vice president at Utility Engineers India Private Limited for central air conditioning projects. But you can see his workload and his engagement with society and with the industry continues to increase. Currently, he holds the role of Director Univac Environment Systems Private Limited for Unitary and Applied HVAC Systems. He's a partner at the Tropical Air Conditioning and Refrigeration Training HVAC NR Professionals and representation of ISHRAE for certification of HVAC equipment. He's a presidential member of ISHRAE and has been a past president of ISHRAE Mumbai chapter as well as the Rotary Club of Bombay Film City. He's a regional lecturer with ISHRAE for the region at large, as well as he's a member of the Technology Task Force with the Ministry of Housing and Urban Affairs. So Vikram has been someone who has been in the industry for many years and has learned a lot and is now constantly guiding us in his various capacities and roles. I have had the opportunity to work with him and see him in action. And apart from his highly capable guitar skills, he also is a great person to talk to in terms of thinking about your own plan in the industry and what's going on and making sense of what is changing in the world, and also a great guide for people in our generation as to how to just get things have more impact in industry and society. So with that, I hand it over to you, Vikram, for this enlightening session from on radiant cooling.
Thank you, Priyank. I look at you and I see a bright future for yourself as well as our society. So maybe have many more inspired people. But you said one thing, and I think that's very important. Whatever we do and whatever we plan to do must have impact. So that's what is going to make all of us more significant and be more beneficial to whom we serve. So I'll begin. I hope you can hear me, Priyank.
Yes, sir, very loud and clear.
Okay, good. So I shall begin by sharing my screen. And here we are. And we'll make it to full screen, which of course is always a challenge because half the screen gets covered with something else. But I hope it happens soon. Should be happening now. Yes, indeed it has. It has, Priyank? You can see the full screen?
Yes, sir.
Yes, we can.
Okay, and you can hear me? I've kept my volume at some reasonable level so that.
Yes, very clear.
Yeah, okay, good. So, our discussion today and my introduction today is on radiant cooling for its applications for commercial and residential. So I'm going to give you a broad overview with some amount of detail, and towards the end I will tell you how DCI can progress further in this part of radiant cooling because it's indeed has a bright future. It is also very much an emphasis now by even the government of India, which I shall tell you about. So here is a disclaimer. The views expressed in this presentation are those of the speaker, which is me, and not necessarily of ISHRAE. This presentation does not constitute an endorsement of the speaker's views, products or services by ISHRAE. So here's a slide, and this slide is from this picture slide is a map of India by its climatic zones. And I'm showing this to you because this has relevance to what we are going to speak about a little later. So a large part of India, the red portion is hot and dry. Most of India, and where you are in Delhi, is composite. That means it enjoys all sorts of weather all the year round. It can be very hot, it can be humid, it can be cool in the winter. And the coastal line of India, which is 7,000 kilometers long, has a mixed climate also, but most of it is warm and humid. and then we have some cold regions. But significantly, what is unique about India and what is special is that we have a very large land mass. We have the seventh largest land mass in the world, which is 3 million square kilometers, and that is one third of the United States and one sixth of Russia. But that being the case, we have almost 18% of the world's population, and so does China. So a large amount of people, 36% of the world's population, live in India and China. And indeed, other countries close to us like Indonesia, Pakistan, Bangladesh, these are all very highly populated countries. But the part about what I want to say strongly about is that a huge amount of India, which is red, and a large part of Pakistan, South Pakistan, which is also going to be shown as red, live in the area where it's extremely hot in the summer and very unbearable for people who don't have comfort. So we must think of ways to provide comfort for them. So India is progressing very, very rapidly in the generation of electricity because the consumers of electricity are only increasing every day. So despite being the seventh largest in land mass in the world, we are the third largest producer of electricity in the world. We produce almost 1500 terawatt hours of electricity, and that's a very large number that I'll show you in the next slide. And that is growing. We are steadily growing because electricity has not been used per capita. Our consumption of electricity per capita is very, very low. It is one third of the world's average, so it is extremely low. So, what is the significance of this whole thing about energy generation? So, we generated 1547 terawatt hours of electricity in a year ending 2019. Obviously, it's gone up then, but a terawatt is a very, very large unit. A kilowatt is 1,000 watts, a megawatt is 1,000,000 watts, a gigawatt is 1 billion watts, and a terawatt is 1 quadrillion watts of electricity, and we generated 1547 terawatt hours of that, out of which cooling energy consumed 135 terawatt hours in that same period, which is a little less than 10% of the energy which India generated was used in cooling. And this is going to rise to 585 terawatt hours in 2038 as projected by the India Cooling Action Plan, which I'm just showing you. This plan, it is good for you to read it, and this plan has lots of thrust areas. But without going so much into that plan, I wish to tell you that one of the major areas is the reduction of cooling energy requirements. And one of the ways to do that is by doing radiant cooling. There are certainly other ways too. And reduction of cooling demand can happen if we do things like natural cooling, and we have ways in which heat doesn't come into a space, and we use ventilation, we can reduce the cooling demand as well. So the India Cooling Action Plan recommends interventions. That means different ways of doing cooling, not the conventional air conditioning with ducts and air and all that sort of thing, for large public spaces. So one of them is indirect evaporative cooling. We'll talk about that some other time. And the other one is structure cooling, where the whole structure gets cooled, such as very old buildings were cooled by evaporative water evaporating around them, or there could be pipes inside them which have water which is evaporating, which indeed is going to be used for the new Parliament House in Delhi. But more about that some other time. But the focus here I wish to tell you is that the India Cooling Action Plan recommends radiant cooling systems for India, and approximately 18,000 tons were done in the period from up to March 2017, beginning from 2008, and that resulted in a big saving of 4 million, it was for 4 million square feet, but it replaced approximately 18,000 of conventional air conditioning in 73 large commercial buildings. So that's very significant. So radiant cooling is well on its way in large buildings in India. Many private sector and the government also is looking at radiant cooling as a very good way of doing cooling, for especially for large public spaces. So let's look at some history. The Taj Mahal, all of you, I'm sure, since you are in and around Delhi or wherever you are, this is one of India's grandest buildings, but it's built on a very large mass base. And that base goes deep into the ground, and it's adjoining the Yamuna River, which flows majestically along its side. And that river gets cold in the winter. It goes down to 5 degrees centigrade, the wet bulb temperature. So it cools this whole very large block, which acts as a thermal storage, and gets so cool that in the whole of the summer, it takes to remove all the heat of the building. And so this building is majestically cooled by radiative cooling, and of course because of the large thermal storage. So radiative cooling has been a very old science. It is historically practiced in many ways in many buildings. And now I wish to tell you, this is not a story, this is a fact. So I'm a very old guy, as Priyank told you. I've spent God knows how many years in this industry. But when I was young and we traveled often, I grew up in Delhi and Hyderabad. So we traveled often from Delhi to Hyderabad to my grandparents' home in a large family. So I had uncles I had cousins, and we traveled in first class carriages. In those days, they look not very different from this. This is not a real picture. I picked it up from the web. But those carriages looked just like this. They didn't have a corridor, and they had 8 berths inside one of those first class carriages, 2 bathrooms, very large space for kids to play around, and very comfortable, So it was nice. It was private. You could make a big noise and nobody would be bothered. But at every station along the way, from Delhi to Hyderabad, as in the hot summer we traveled, the coolies, the guys would bring inside tubs like this, maybe 2 tubs, and put a large block of ice inside this tub. And this ice would be about 4 feet by 1 feet by 1 foot. So I'm just doing some little calculation in front of you on my phone. So 1 cubic feet of ice weighs 62.5 pounds. So this size of ice would be, let me just do this calculation for you. So this block of ice is 16 cubic feet. That's 4 by 1 or 4 by 2 by 2. Let's just say that's the size. So 16 cubic feet into 62.5. That is 1,000 pounds of ice, which is about 500 kilos. So 2 of them into 2. 2,000 pounds of ice in that carriage over here. And the ice is a great store of energy. It has 144 BTUs per pound. So I'll multiply that by 144. So I get 2,88,000 BTU hours, and I divide that by 12,000. And I get 24 ton hours. That means it will provide 1 ton of air conditioning for 24 hours, or 6 tons of air conditioning for 4 hours, equivalent. So if we put on the fans in this carriage, which aids the cooling, so then we used to feel very comfortable, and it used to get very cold, and then we would cover this up with the cloth which was provided along with this tub. And so the journey was very comfortable. But the point is that this was all radiative cooling. Our bodies and the carriage gave up its heat to this block of ice which melted, and 4 hours later the coolies came and took it away and put 2 more tubs of ice. And so it was a very I wouldn't say it was a great way, but it was a very innovative way of cooling. So let's come and see what is practical in radiative cooling. So in radiative cooling, heat flows because heat flows from hot to cold by the principles of radiation. Radiation is a very powerful source of movement of heat in the world. There's conduction and there's convection. But radiation is so effective because it's proportional to the delta T between the cool surface and the warm surface, the difference of that to the power of 4. So you can see if the delta T is higher, the radiative cooling is much faster. And of course, it depends also on the area A. So the larger the area you have, the more cooling effect is there. And so you can calculate how much cooling you want. And so because this kind of cooling can only take out sensible heat, it cannot remove the latent heat. And because it's all well contained, you cannot get fresh air. So you must have another small system to bring in fresh air, which can take care of the ventilation and can also take care of bringing in cooler air to remove the humidity. So you have a combination of things when you do radiant cooling, which is nice. So radiant cooling, and this is just a picture, and it's based on the principle of heat absorption. It can be radiant heating, it can be radiant cooling. Most of the cold countries in the world, like Europe, use radiant heating, so they heat up the floor or the ceiling, and so then the coolness of that whole space and the people gets radiated to the heat, or the other way around. So in thermal radiation, what happens? The cool surfaces have lower vibration and the hot surfaces have higher vibration. It has more energy, and therefore the heat waves keep coming down and the cool bodies get warmed up by electromagnetic radiation. And the opposite happens when we do cooling. We have cooler particles. You might have a cool roof, you might have a cool floor, and everything flows very well without making any noise, without making any sound, without air moving around. So radiation is the form in which you get heat from the sun. That's the most powerful example of radiation that we know. So And also, of course, the radiation flows in straight lines. If there are obstructions, then the radiation will not happen. It can transmit itself through to transparent surfaces. We can get the sun's heat through our windows, but if we shut the window, the radiation will stop, but it will heat up the wall, and then the wall will transmit its heat to us by convection. So the infrared spectrum of the whole electromagnetic spectrum is the area where all this transfer takes place. So it's not in the whole range, but it's a fairly large range of the spectrum, and the wavelength ranges from 1 to 0.38. And so in that range, we do all the radiative cooling. And I told you about this. A light bulb also can emit heat if you go close to it. And of course, the sun does the same thing. So this is just a picture. This is not a picture about radiative cooling, but it's just a thermal image of a particular room. This is this is a room probably in a colder part of the world. So its windows are 65 degrees Fahrenheit, and its roof is at 72, and some other wall is also quite cold. And so if you take a thermal image with an infrared camera, you will get an image like this. Now, what about comfort? So, we as human beings perceive comfort with our sensory organs. So, we feel hot, we feel cold, and sometimes when it's very cold, if you go to the cold parts of India or the cold parts of anywhere in the world, and it gets close to 0 degrees centigrade and below that, your eyes will start watering, your nose will start watering, your ears will start paining. So, if you don't wear a hat, woolen hat to cover your ears, you will be in a very uncomfortable condition. And of course, our hands also start feeling cold, so we start wearing gloves. We must wear good socks and shoes in the winter. So these are all the sensory parts of the body give you that impression of heat and cold, and your body reacts accordingly. So what is thermal comfort? It is a state of mind. We are satisfied with the environment. Some of us are more comfortable with a wide range of temperature. For example, I can say that about me, because for years I've been outdoors, and for years I've been in cold places of India and here and there and all. So I'm not at all uncomfortable in a large range of temperatures from hot to cold. But some people have got used to a much narrower band. They feel cold faster, they feel hot faster, and so on and so forth. So the average person, there's no such thing as an average person, but a large number of people being satisfied with the condition means that it is comfortable. So this is just a caricature, it's a cartoon, that if 1 foot of yours is at the very hot condition and one is at the cool condition, are you going to feel the average of that? No, that's not the case. Each of these things will have their own tactile response. So you must have, so this is bringing us to this whole thing, that there should be an operable temperature, which is what that person feels. So let's think about and stop about this. Suppose this was a room. Suppose this is a room and you're seeing it in cross section, and this is a very hot surface because it's a window, and it's a glass window, it's facing west, and it's getting in a lot of heat. So if this guy goes and sits over here, even though this room may be cooled by air conditioning, but because that window area is very hot by radiation, he is going to feel a different operative temperature than a person who's sitting somewhere inside. Similarly, if for some reason that floor is very cool, then he is going to feel a different operative temperature than one who's sitting on the sofa high up from the floor. So these are all the whole things about thermal comfort, that it is dependent on many things. So our body is, it has many things which can affect its feeling of comfort. One is the air temperature, which is the most common thing we know, and we can easily measure it with the thermometer. But remember, what you measure as the temperature in the air may not be the operative temperature of the person who is experiencing what you've just measured, so which I will come to a little later. And there's the radiant temperature of surrounding surfaces. You might have a very hot iron. Your wife might be ironing your clothes. If you're a lucky guy, that may happen with you. So there may be some kind of cooking going on over there. There may be a glass which is bringing in lots of heat. Humidity is a big factor. So dry air, moist air, these all make a difference and to the level of comfort. So higher humidity at temperatures up to around 35 degrees centigrade, 34, are not very uncomfortable. Right now I'm in Mumbai and the temperature is around 32 degrees, but the wet bulb temperature is very high. It's 28. That means we have very high humidity now in Mumbai. but I'm not uncomfortable. I'm putting on the fan, so air motion is making me comfortable, and my body is not able to remove heat by evaporation because the wet bulb is very high. But I'm getting comforted by air motion, which is making the apparent temperature lower than 32. And of course, I'm inside, so it might be 30 degrees over here. And so, a radiant cooling system can be controlled by putting it on the ceiling, and it can take care of the air temperature, it can take care of radiant temperatures, it cannot take care of humidity, it cannot take care of air motion. What about dust, acoustics, and aesthetics? So, because we don't have air and motion in a radiant cooled space or a radiant heated space, dust is very little if you keep the places closed. Sound is absolutely absent if you keep the places closed. Of course, you might have a fan and that will make its own sound. The aesthetics are beautiful. You don't have ducts, so your ceilings can be very high. You don't have grills, you don't see anything, so it's an architect's delight. Of course, odors, these are not related. They cannot be controlled by the radiant cooling system. And the lighting also is not controlled. The lighting adds beauty and value and visual effect. It may also add some amount of heat. What are many of the advantages of a radiant cooling system? There are many advantages, and I'm just going through them quickly. You can see this on the screen. I will encourage Priyank and Tapas to share my presentation, anybody who wants it. I have one or two references which are PDFs, so if you get it, you can read more and you can study a little more about design. So, of course, there's thermal comfort, which of course there is. There is no sound, it is very pleasing. Zoning, we'll come to this little later. With a radiant cooling system, with water being supplied, you can shut off, you can put on, you can increase the cooling in some space, you can decrease it. It's a great energy saver. You'll come to see why. One of the simple answers to that question is because there are no motors for fans, so that's a big energy saving. Also, we are supplying water at higher temperatures, so the chiller is also going to save energy. And there's no duct work, very low maintenance cost. There's no dust. And of course, if you're doing radiant heating in the winter, because you're adding heat, you can take care of the humidification, which of course is by bringing in fresh air. That's slightly different from the radiative cooling. So what happens about the thermal exchange and radiation cooling? So 45% of the heat removal to 50% is by radiation. Convection is only 15 to 20%. There is some amount of evaporation. And of course, if the surface is cool, then there is going to be some amount of conduction. But most of the time, we wear footwear. So there's not going to be much conduction unless you're with bare feet, in which case there will be. So, what is the point of this whole slide? Is that when you do radiative cooling, that means you cool the floor or you cool the ceiling. You can also cool the walls, nothing wrong with that. Then you're going to have most of the heat removable by radiation. Why is there convection? Let us talk about that. Convection happens naturally because when surfaces are cool and some other one is not so cool, there will be automatic air currents generated. So convection is going to take away heat. Much of the radiation is a direct path, and convection is a slower path of air and motion because of temperature differences. And if you do air conditioning, then radiation is going to take care of a very little amount of that. Because the grills and diffusers are cold, there's going to be radiation because of that, because they are cold. So some amount of heat transfer will take place to that cold grill. But most of the cooling is by convection, because that's how air conditioning with air does all its work. Most of it is by convection. And of course, because of this good air motion, we feel comfortable because our body loses heat faster by evaporation. And so that's a great thing. And that's why we cool faster. If you get much more air motion, evaporation takes place much faster and you feel cooler faster, which is why in an air conditioned room, if you put on the fan, you might start to feel uncomfortable for two reasons. One is high evaporation. The other thing is the cold air might come directly on you. So that can also happen. So so the comfort of radiant ceiling. So let's talk about the radiant ceiling. And this is the heating picture. This is the cooling picture. So the thing is, the point about both these pictures is there is a reasonably small amount of delta T between the top to the bottom in the apparent temperature in the room, in the operative temperature, because there is no air in motion. There is no cold air coming out from a grill and return air going out from somewhere else. the whole space becomes kind of even in temperature. Okay, and whereas that was for heating, and for cooling also it is simpler, also in the same way, because the roof is cool. It's at 65, which is around 16 17 degrees, or maybe 18 degrees temperature the roof is, or the ceiling is, with all the pipes over there, and the whole room becomes a comfortable 72, maybe 21 22 degrees centigrade, and so the whole space is even in cooling. That's the biggest advantage. And whereas if you do it from the floor, it's also very similar. So we'll talk about whether we should do it on the floor, whether we should do it on the ceiling. To give you a very short answer, both of them are good. It depends on what is convenient for you, what is cheaper, and so many other things like that. And so here also you can see a very narrow band of temperature difference. And what happens with air conditioning? So this is a typical low mounted fan coil unit, which used to be quite popular some time back. The good thing about this unit is that the cold air is from a lower level, so it doesn't have to, you can get the comfort of cooling much faster, because really speaking, we are all going to be at 6 feet above the ground and below, and what is above us, we are not bothered what happens over there. So this makes the cooling faster, but you can feel a little uncomfortable. This is the heating mode, and the cooling mode, you can feel a little uncomfortable because the cold air is coming out from the top and the returner is going back. So there's not such even conditions of temperature. So that is the disadvantage of the conventional air conditioning as compared to radiant cooling. So here is the same picture. It is trying to show you the uniformity of the cooling right across the human body, and an average temperature. The delta T is very small, and the flow gives you a slightly higher delta T, whereas in conventional air conditioning, the delta T can be quite high. It's cool because this is a low supply air unit. So you can get very cool at the lower level, and you can get warmer at the higher level if you're standing. And if you're continuously standing, you're going to experience that high delta T. Of course, if you're sitting, the delta T is going to be much smaller, right? So in conventional air conditioning, some guys who are closer to the air conditioner might feel cold. Some guys who are the right distance away might feel very comfortable, right? And if you do radiant cooling, then everybody is quite the same level of comfort. Acoustics, of course, I won't spend much time on it. The simple answer is that the outdoor sound, of course, is going to come in both cases of radiant cooling as well as conventional cooling, but you're going to hear the sound of the air conditioner inside. So I'm just stopping for a minute over here to make a comment. It takes some time for people to get used to and to get comfortable with radiant cooling, because they don't hear the sound of anything. And so they wonder what is happening over here. But after some time, they feel quite comfortable because the operative temperature surrounds them. And when they first enter, they might not feel that operative temperature because their body is warm. There's no cold air coming from a grill. You don't see any grills. If you cannot see a grill, you're not going to feel psychologically comfortable. So radiant cooling takes time for people to accept it. There are some companies, I visited the offices of Infosys in Hyderabad. They did one whole big building with conventional air conditioning, another one with radiative cooling, and they measured the whole thing over a year. But I must tell you that in the place where radiative cooling is there, Infosys decided to put fans in all those spaces where radiative cooling is there to increase two things. One is air motion, and secondly, to psychologically please the people working there that they have air in motion. But the best thing is that many times of the year in Hyderabad, it is not at all cold. Sorry, it is not at all hot. It's very comfortable temperature, and then the fan works very well, and the radiative ceiling or the floor can be at a much higher temperature, and still everybody feels comfortable, because by now everybody's got comfortable with that kind of comfort cooling. So I took some of these slides from this company, the Building Energy Efficiency Project, which is BEEP. It's an Indo-Swiss project. They're advising the Bureau of Energy Efficiency and EESL and many other organizations. And they conducted a nice series on radiant cooling training, which I attended in Hyderabad at IIIT some years ago. And so I took these slides from some of those presentations there. So what does it say? Where is it applicable? Anywhere radiant cooling is applicable, where sensible loads are more dominant. and where indoor humidity control is possible. That means you do it with a separate system. So the most common applications are office buildings, educational facilities, healthcare, government places, laboratories, but not in spaces where sensible loads are not dominant. For example, not a good idea to do it in toilets, kitchens, and bathrooms. Not a good idea to do it if you're constantly opening and closing doors and allowing huge changes in humidity. Not a good idea if the dew point is very close to the operating temperature as it is in Mumbai today. The building tightness is to be good, right? So this is also important. So you have to see there are some limitations for the application of radiant cooling, but they are not serious limitations. So later on, I will tell you in continuation of my program, you should invite the the chair of ISHRAE's technical group on radiation, Madhusudan Rao. He's in Hyderabad and he has a company which does what do you call it? Solar, electricity generation, and so on, renewable energy. Oh, he also does a lot of radiant cooling projects. So he has got very good practical experience to tell you all about the designs and the work which he's done. He's also done some wonderful projects for small malls in Hyderabad, which is, I think, a great achievement. And there he removed all the split air conditioners and put in radiant cooling and a small amount of DX units for the heat removal of moisture. So quite practical. So what are the differences of air systems, which is conventional air conditioning and radiant cooling? So in space cooling, we supply air to take care of the removal of all the sensible heat and the latent heat. Whereas in radiant cooling, the only air is coming from a dedicated outdoor air system. For example, so let's talk about this. In the typical space for comfort air conditioning, 80% of your load will be sensible, most likely, and about 20% will be latent from people and from the fresh air which you need. So the 20% load is all that you need to provide. So let's say a place has got a total load of 10 tons. So the likely requirement of refrigeration load for removing the humidity and bringing in fresh air is likely to be only 2 tons. So you can have a small treated fresh air conditioning system. That's the easiest way to do it. Or you could have heat recovery systems and so on and so forth to bring in heat and save some energy. But that's a small amount of energy you'll spend doing that and a small amount of fan power to produce that air. And there will be no air required in the radiant cooling system for the radiant cooling. And what about the chill water supply? So in air conditioning conventional, we supply water at 5 to 7 degrees centigrade because we have to remove humidity. So therefore, our cooling coils have to be cooled to much below the dew point. Then only we can remove the humidity. So that's the thing about air conditioning. We have to cool the coil till well below the dew point, and thereby we remove humidity as well as we remove the sensible heat. Whereas radiant cooling system doesn't require to be so cold. The temperatures of the surfaces in radiant cooling are 20 degrees, 21 degrees, and then the room becomes 24, 25 operative condition. So we don't have to supply such cold water. We can supply water at 14 degrees, 12 degrees, and this is the kind of range which is there for the radiant cooling system. Of course, the dedicated outdoor air system, if you have another chiller, this is what you will need. You can also put a DX system for the treated fresh air system, which can be without a chiller. So the chiller operates at much higher suction conditions. So its energy consumption is so much less to produce this kind of water. And of course, in both the cases, your operative temperature, that means the perceived temperature of the person in the room, the average person, around 25 degrees for which you may design. And the space air temperature in the conventional system is going to be lower because remember, it has to pull out all the heat of sensible as well as latent. With the radiant cooling, the operative temperature, not the operative, but the space temperature is higher. It doesn't need to be so much cooler. And the surface mean radiant temperature. What's the meaning of this? That means surfaces. If you feel surfaces in that room, they are likely to be around 26, 28 because the cold portion is coming from the air. It's not from the surfaces. Whereas in radiant cooling, the surfaces which are radiantly cooled by pipes, they are going to be at a lower temperature. And the air quantity, we talk about this. This is the same thing as what is happening over here. Right. So the energy savings are very, very tremendous. So this is an actual measurement which was done by this BEEP organization in a real project. And so you can see that the chiller savings are a huge amount. They are 40% less, and the fan energy is also a huge percent less. Of course, some energy is spent for doing the DOAS. So we must add it back to the savings here. But that you can see is only 20% of the whole load. And so even that, if it is well designed, your savings are going to be an average of 40% over conventional air conditioning by the radiant cooling. So the investment is in the system, the investment is in doing the execution, the investment is in time. It's going to take longer to install a radiant cooling project, but if you work early with the architect and as the building is done and as the customer allows you to work, after all, no building is constructed in 2 days or 4 days. Building takes months and years to construct. So if you get involved with that project as a part of the civil construction work, then you will be well on your way to doing the radiant cooling project well. Of course, retrofits are always possible. So because you have don't have ducts, you can have much higher ceilings, and the architect has the freedom to do whatever he wants in that ceiling without worrying about your ducts and grills over there or putting some boxing somewhere else. So these panels are embedded in the ceiling. This is talking about ceiling. They could also be floor radiant ceiling. And so one of the good things about radiant cooling is the ability to do zoning. So you have this bulkhead and these distribution systems of cold water pipe and hot water pipe. And so you can separate it, and then you can have controls over this whole thing. You can control it remotely by a management system, and you can do temperature control, you can do occupation control, you can do time control, you can get all the information you want. And the PEX pipes, which are the plastic pipes and so on, which are going everywhere, if it is floor or if it is ceiling, those ones are connected back to these manifolds, and you can have a whole well balanced system. You can shut off, you can put on, you can increase, you can decrease. So just like I would compare this to a VRF system where you can control individual spaces separately. I'm making that comparison because it gives so much of flexibility as compared to a ducted air conditioning system for a large space. There is less flexibility, whereas this offers a huge amount of flexibility, right? And also at different times of the year, you can control the whole amount of air conditioning effect of cooling. So the zoning is shown over here. You have the manifolds; those are going to different parts of this space, and so on and so forth. You may be doing it for an apartment set of apartment buildings. So apartments are very good applications for radiant cooling, and they will work very well. Imagine, so let's talk of an average apartment, which may be 1,000 square feet or 1,500 square feet, whatever it is. And imagine that while the building is made, the whole floor is got pipes inside it, and these are controlled to a cold water system, which is giving it. The whole house will get comfortable and cool, and then you may have one or two split air conditioners around, which will work sometimes when you want to reduce the humidity. And so it's very easy and very comfortable. And because zoning is allowed, apartments can be switched on and switched off. The apartment owner himself can control the amount of flow. And so there's a variety of ways. Of course, and this is all in the future. Presently, commercial applications are far easier to do. So as I said before, that the energy saving is huge. And why does this energy saving come? It comes for two reasons. One is from the chill water temperature being higher. The other is the pumping cost of air. So water has, because of its high specific heat compared to air, it has 3,500 times the ability to transport coolness in much smaller pipes, and that is transported by pumping water with the pumping system. And so therefore you save a huge amount of energy because you're transporting water instead of transporting pipes. Of course, in conventional air conditioning also we have fan coil units, so it's not that it is radiant cooling is very unique in that respect. So fan coil units like hotel rooms, they have pipes coming everywhere. So you don't have to put big ducts, and all the cooling energy is coming through that pipe, and it is released in the fan coil unit in the conventional system. In the radiant cooling system, this pipe will supply a whole grid of pipes on the floor or on the ceiling, and thereby produce the cooling. Okay, so Lawrence Berkeley Labs in the United States did their experiment, and it did real comparing it with variable air volume systems, and they found that the 30% on the average. So it is a shall we say a conservative uh, figure which they actually got by checking out everything. And so the energy saved ranges from 17% in the cold, moist areas to 42% in warmer, dry areas. So you can see that there is the savings are more and less, and depending on the climate zone of where you operate. So there are lots of loads in the building. So fan and motor power, a huge amount of saving comes out of not having that. And of course, there are pumping costs, and the air transport load, which is 9.3% in conventional, becomes very small over here because of the dedicated outdoor air system. And the load from the lighting also can decrease. The load from the lighting decrease or increase is I don't actually know the answer to why the load from lights is less or more, but I have to think about that, and maybe you can also think about that, and maybe we'll answer this question in the question time about why this picture is showing loads from lighting to be higher in a conventional system and less in the radiant system, unless they're allowing more light to come in naturally. Anyway, so compact design and less ductwork. So ductwork becomes much smaller because you're bringing in only 20% of the air or less for bringing in fresh air. And of course, the ceiling height you get much more. So you can add one floor for every 5 floors. So that's good. So you are going to save a foot or a foot and a half on each floor because you don't need it. Or you can have higher ceilings. You know, there are tall guys who must be attending this program. So in many flats in Bombay, if this tall guy raises his hand, it might get chopped off by the ceiling fan because the heights of flats are coming lower and lower. They are hardly 9 feet high, so the fan is probably at around 6.5 feet high or 7 feet. So if the guy puts his hand up, he's going to touch it. So that's not a good thing, isn't it? So if buildings could be with higher heights of 10 feet, 11 feet, that would be so much better for everything, for the appearance of the house, for safety, and also for design. You could also have some amount, if you have a tall floor, you could put incoming windows at a higher level, or you could have very high windows, which will add more beauty also. So here it is. So we have architecturally pleasing levels of greater than 9 feet. So that's the important part. And because you're able to get another floor, because of that saving of ducts, it's going to be good. Of course, this applies largely to commercial buildings which are planning to do ducting. It may not apply to residential buildings, but even residential buildings, if they switch to radiant cooling, they can have this advantage. So dust is, of course, a good thing. There is no dust and there is no air movement, so there is no dust movement, and there is nothing happening. The dust is not in touch with the slab if it is above. If it is below, of course, there's going to be dust from somebody's shoes and this and that and the other, but that is easily clean because nothing is on the surface. You're going to have a smooth surface. And so over here, what is it saying? That cold air moves down. Of course, it does. So in the radiant cooling system, what are we showing over here? So we are showing some conventional systems for doing your ability. So first of all, there is the cooling. This cooling system is shown represented as a DX system, but this is wrong. It should be actually cold water which is coming and producing itself. I'm sorry. I have to correct myself. This is actually showing the dedicated outdoor air system for the refrigeration unit, which is going to be doing removing of this latent heat from the space. So that's what it is showing over here. So radiant cooling terminals. So radiant panels are heat terminals. They exchange heat with the indoor environment, whether it's heat or cool. And they could be made, the panels could be made in cast in gypsum, plaster of Paris, or MDF, which is a synthetic material like wood, or they could be in material or in metal, or they could be simply cast in the floor with embedded pipes, right? So the ceiling versus floor response time. So what happens in the floor? In the floor, you have a finished floor of a building. You will have to create a scrid of concrete so that you can bury the pipes and cover them up with a smooth surface. And because there is some time for conduction from the cold pipes to the top of the surface, it is going to take time for the coolness when you start the system to get cool on the upper surface, so it will take time. Whereas if you have a radiant ceiling, because the thickness of the gypsum of the metal is very, very small, it will be very quickly allowed to transmit its cooling. So the time is going to be saved, but that may not matter very much if you are starting off your cooling in the morning, and it will be and soon it will be the same whether you do this or you do that. But this is the difference about the time it takes. That's what it's trying to say. And so the same thing over here. So the temperature different. What is the difference between these two? 30 minutes increase the surface temperature, 1 degree of conduction, convection, surface response time. Okay. One picture was for the surface response time, and the other is for the air response time. So obviously air is going to take much longer. Once this gets cooled, then the air will get cooled, and once this gets cooled, then the air will get cooled. So your response time for a floor type of radiant cooling is probably going to take an hour before you will feel comfortable inside the space once you start it. So that is the thing which you will have to bear with. But really speaking, it doesn't matter if it's a commercial space, right? So when you have a new structure, what are we going to do? Are we going to do chill water into the gypsum type of ceiling? Are we going to do walls which we are going to cover up? Actually, it is not so easy to do this work on walls unless they are completely continuous walls without windows. Because wherever you have a break in the window, you'll have to have a separate system of piping and so on and so forth. And that is possible. Maybe in some commercial spaces, there's a large amount of straight wall, which is a partition wall. So you can do it well in that. We could even think, as I'm thinking now, that we could get precast partition walls with pipes embedded in them, and we just join them together when they come to the site, and then we connect it to chill water. And that may be a very quick way of doing a project if you have a completely open floor and you want to put in the system in the form of walls. But I'll tell you the problem with walls. The problem with walls is that some people will be close to the wall and some people will be very far away from the wall. So the people who are far away from the wall, they are going to get the effect of radiation far less. Whereas if it is the floor and the ceiling, everybody faces the same floor, everybody faces the same ceiling. So the evenness of the radiation effect is far better if you do it on the floor or on the ceiling. Additionally, you may do it on the walls if you have space for that, but it's going to be cumbersome. So here's what is he showing, that they have panel cooling system. So here the panels have come ready-made. They are prepared panels. There are manufacturers of panels. There are many now in India. I'm just going to speak about one of them in some time. And so those are easier to install, quicker to install. Of course, their effect is a little less than doing it on the floor because they have to be joined. They have to be joined one to the other, one to the other. The pumping cost is also going to be slightly higher, but they look very elegant and they are nice to fit and nice to install. And you don't have to do this whole amount of ground preparation of burying pipes and covering it and so on and so forth, right? So you can see it over here. But there's one advantage of doing it on the floor. This is what I want to tell you. The advantage of doing it on the floor is that if at some time of the year, for some reason, your water becomes very cold and your control is not so good, this is not likely to happen, and then the dew point is reached because somebody allowed moist air to come in, then moisture may condense on that cold surface. And you might see moisture on the radiation panels, the floor. But then it's very easy to mop the floor, right? Just as we mop our homes or our offices, you can quickly wipe that. You will quickly see it. It won't cause any damage because it's on the floor. So we must make a floor which is sloping a bit. Whereas if that happened on the ceiling, it is going to be dripping moisture down. But I just wish to let you know that don't be alarmed by what I'm saying. This doesn't happen. What I am talking about happens very, very rarely. But that is the one advantage of doing it on the floor. Also, it is much cheaper to do it on the floor because you're just burying those flex pipes and there's a cost of finishing the floor. It's one time. And the maintenance also is never going to be there because they are buried forever. Whereas over here, you have to check to see that the connections are perfectly good and there are no leaks of any kind, right? So what are the factors which govern thermal comfort? We're coming back to this now about operative temperatures and so on and so forth. So there are personal factors. So one of them is the metabolic rate. I told you some time back about it. Some people feel cooler, some people feel warmer. Older people feel cooler faster. Women, mature older women feel a little cooler than men of the same age. But I think young girls and young boys have the same metabolic rate because they're equally active and energetic. What clothing you wear determines your metabolic rate if you're well covered. So we must dress for the season of the year, which is a good thing, and that is adapting to the weather. But of course, there are other environmental factors. So what is the mean radiant temperature? What is the air temperature? We'll see about all of these. What is the air velocity? What is relative humidity? So these all factors also determine how comfortable we feel, all of them together. So here I'm talking about what is radiative temperature. So without going into this formula, let's just look at this picture. So here's a guy. He is close to one cool wall, which might be a partition wall, and maybe the neighbor is room is air conditioned. He is also close to a hot wall, which may be glass exposed outside, or it's exposed wall which is getting very hot in the afternoon summer. So he is going to feel the effect of radiation. His body is going to absorb heat from here. His body may lose heat over here, and both the things may happen depending on the balance. So that is what the effect of radiation exchange is. It's happening all the time. We don't even realize it. It is happening all the time, but because there's such small deltas are happening, the effect of it is what we completely, in the end, come to perceive as our operative temperature. So the rough approximation for mean radiant temperature is like this. It's the sigma of the area into the delta of that temperature, what you can measure. If you put a thermometer on the surface, you can measure the temperature. So you take the sigma of all the surfaces, up, down, side, here, there, everything you take. If there's some large table which may be hot for some reason, you can take that surface also and add up all of these and divide it by the sigma of all the areas which you took. And so that average is what we call the mean radiant temperature of the room. Nobody actually perceives this. It is the room's mean radiant temperature, which you have to measure by measuring the temperatures of all the radiating surfaces. And then you get the mean radiant temperature. Then there's an operative temperature. That is what the person feels, and that's what he perceives. And what is that operating temperature? That is, first of all, the L is the mean radiant. This is not Q, this should be theta. So theta is the Greek alphabet for temperature. So the theta L is the mean radiant temperature, which we talked about the last time. So there's a mean radiant temperature of that room. And then there is an air temperature, which you can measure with a thermometer in that room. And so the average of both of these is what is the operating temperature. Quite often, these two might be very close to each other, quite often. That is, if you have surfaces which are quite evenly in temperature, then these two will be very close to each other. If you have surfaces which are very getting hot, like a hot roof which you have not insulated, or a hot west wall or west windows, those will be very higher in temperature, then these will be a little different. Okay, so when we are talking of two separate rooms, one is cooled by conventional air conditioning and the other with radiant cooling. So while the mean radiant temperatures are going to be different in this room, why are they going to be different? Because we have got surfaces which are hot and cold. And the air temperature also here is much cooler. It is much cooler because we are blowing a lot of cold air to remove the humidity as well as the temperature. And the person feels an operative temperature, which is what he perceives where he is. Whereas in the radiant cooling space, that person will perceive an operating temperature based on the calculation which you did in the previous slide. So it is very likely in a radiant cooling space, in a cold space, even the walls and surfaces will become even in temperature after some time, unless one of the walls is constantly getting too much of heat. That is, it is facing west and the summer heat is coming in. So we must be in a radiant cooling space. It is good to try and bring down the temperatures coming in from surfaces, and that will save you energy for all time. So if you insulate that particular wall, if you use windows which are well shaded, then that's going to happen. And in any case, you will bring down the heat load substantially, which will also bring it down for a conventional system, of course, right? So Here is an example which somebody has done. Actually, if I had to do a workshop, then I would make you calculate this whole thing over here, which is actually doing nothing else but these calculations. We are taking an example of this calculation and the next calculation, and we are calculating it for two different rooms which have these different conditions, which have different ceiling temperatures, which have the same floor temperature, and which have the same wall temperatures. So we find that the operative temperatures are slightly different but almost the same, but the mean radiant temperatures of these two rooms is going to be different because the ceiling temperatures are different. So we can calculate this type of thing for different rooms if we have do a practical experiment. So while learning about radiant cooling, whether it's a student or whether it's somebody who wants to get into the business, it's good to be able to do all these calculations inside a space before you decide to do radiant cooling, because you have to see, is there any one particular surface which is contributing to so much of heat in that space, then that is going to disturb the effect of radiant cooling, because it will constantly bringing heat and it will change the mean radiant temperature of that room. So we must not have very hot surfaces in spaces which are radiant cooling, which is why it's done for commercial buildings where most of the areas are internal. And the external areas, it is better to do it either by ventilation, evaporative cooling, or conventional cooling where you don't have to cool it so much. It is mostly corridor areas and things like that. And of course, if it is a large amount of glass area which is exposed, then those glass areas should be on the shaded portion of the building, on the north side, the northeast side, and things like that, less on the west side. And east is okay because in the east side, the sun is very quickly, after 10, 11 o'clock, it is going to go up and you would have an insulated roof. So here I'm showing you a picture. So I would stop here to ask Priyank. Priyank, is this going on fine till now? Okay, anyone can answer me who's listening. Tapas or Priyank? Hello? Hello?
It is going on fine, sir. It's fine.
Okay, okay, very good. I just want to know because I sometimes I want to tell you, Tapas, some maybe last year or sometime I was going on talking and nobody told me that they can't hear me or they can't see anything. So that's why I asked from time to time. So good, good. So if it is going on fine. So I'm just talking. By the way, this is not a commercial presentation for about Infosys. I'm just mentioning that they make panels of this type for their in-house use because they have very large spaces to do the cooling all over India. And so they develop these panels because they can quickly get the radiant cooling system installed without doing it on the floor. They're doing it on the ceiling. So they develop these panels and they tested them so that they know how they perform. And this is what they found. So there is a standard. There's an EN standard for these type of panels by which you can specify it and which you can measure how it produces its flux, which means the heat energy. So, so they claim that it's producing very good capacity with less cost compared to current solutions. Maybe that's true, maybe it's not true, but that is a matter which we can find out by the specifiers of who are making such panels. So it is producing and it is able to deliver 193 watt per meter square at 10 degrees delta T. What is delta T? It's a difference in temperature between the entering water and the average room temperature. So, for example, the entering water might be at 11 or 12 degrees centigrade, and the room might be at 21, 22. So that is 10 degrees, right? So that is a typical temperature difference between water entering in a radiant cooling system and the room condition. So at that delta T, it's producing this much watts per square meter. So for those of you who are more familiar with the BTUs and square foot, old guy like me, so then the system says it is 60 BTUs per hour per square foot. So let's talk about what is this going to do. So if you have, for example, 1,000 square feet of space, so 1,000 square feet will get 60,000 BTUs, right? Which is about 5 tons, which is quite good enough for that space. and you know that 5 tons is not going to be the full load. Maybe 1 or 2 tons will be the latent load, which you can bring in a separate system too. So these panels are quite good. So that 1,000 square feet of space, if you put these panels, you can remove all the sensible heat quite easily with these panels developed by this company. And I'm sure there are many other panels. By the way, I'm not a much of a contractor for radiant cooling, although I will tell you at the end I'm doing something else in radiant cooling as an experiment with some friends of mine. But there are many contractors and companies today providing very good radiant cooling solutions, and one of them, without promoting him, is the chair of our ISHRAE technical group, and he's done a lot of projects. The good thing about him is he's willing to share all his knowledge. And I had the pleasure of listening to him at some seminar, just like I am doing for you. And he gave a lot of practical knowledge. So it's good if your chapter calls him also to speak to you. And the other good thing, I'm talking about something now, is that the technical group of ISHRAE, and I hope all of you are members, even if you're not, you can become one, or you can get that. What I'm talking about is that radiant cooling technical group is very soon coming out with a wonderful guide to designing and installing radiant cooling systems for India, because there are lots of things about India which are very specific in terms of climate and so on and so forth. So that book will be out very soon, and also ISHRAE is planning to have a course for doing for understanding how to do radiant cooling design. So that will be a wonderful opportunity coming up for us some months ahead. In the meanwhile, you're most welcome, if you have a smaller group of people who would like to know more about radiant cooling, to invite Mr. Madhusudan Rao to speak to you about practical ways of doing the radiant cooling, which I am talking to you about in a very general sense. So they did, this is a lab, what do you call it, output for what they did. They measured it in the lab and to the standard. So I think it's a good thing because they did all the testing and the performance. And so you are very sure and assured. As you can see, as we get to 10 degrees delta T, it is coming close to 200 watts per square meter of performance. So it's a good panel. And of course, it is based on entering water temperature and area. So this is just a picture of showing how it looks when it is completed. It looks very good. And you can see all the heat is going up from the people. This might be a typical Infosys office. It could be any office. And the heat is nicely going away. So imagine if we had a few ceiling fans also running. In fact, I can see one fan. I'm not so sure if this is a fan, but it looks like a fan. Whatever it is. My pointer seems to have disappeared. So here it is back. Okay. So dew point. Dew point is very important to know about dew point because condensation will occur if the ceiling surface goes below the dew point. But not to worry. The technology has advanced so well that we have dew point sensors. And so once we know the dew point sensing, if the air temperature outside is coming close to the dew point, you better start making those panels a little warmer so that it doesn't reach the dew point condition where air will condense on that panel. But be sure that radiant cooling projects are not going to admit a huge amount of outside air which is not treated. Of course, they are bringing in outside air with the dedicated outdoor air system, but that is treated outside air. And so if you suddenly open the window, of course, outside air will come in, and that's not going to be a good idea. So in such places, I suppose windows don't open or whatever else they do. Or you can beat all of that by having the dew point sensing to have good control. And I'll show you a picture of that. So this is a psychrometric chart. We are not going to start a class on psychrometrics, but in Bombay today, in Mumbai, this is the temperature dry bulb. This is the temperature wet bulb. So you can see the delta between dry and wet bulb is very small. It's only 4 degrees centigrade. That means we have high relative humidity. And our dew point is 27 degrees. Very, it is very close to the wet bulb. So it is, if you bring in outside air into a room which is radiant cooled in Mumbai today, is not going to be a very good idea because condensation will take place. So this is when we know. So right now, what is the answer to this problem? There is a simple answer. It is not hot in Mumbai today at all. It is only 32 degrees, and that is outside. So inside my home, where I'm sitting, I have a thermometer behind me, which if you see the picture, anyway, it's there somewhere. I read it some time back. It was 29 degrees centigrade, which is a very comfortable temperature. And with the fan on, I think I'm perceiving around 27. And so as ISHRAE came out with its guide last year, which is accepted by India, that we should be between 24 and 30 based on high and low humidity and so on and so forth. So anywhere from 24 to 30 is very comfortable. So there would be no need to do radiant cooling in my home today at all. So the question of having this condensation would not arise. Or we would have very mild radiant cooling to remove the heat of my body, because all the walls in my house are not hot at all. It's been raining for the last so many days, so all the walls are very cool. The sun is not shining, so there's no solar gain. So therefore, gradient cooling is the best solution because it applies to when it's needed, right? Okay. The key component of a radiant cooling system is to avoid condensation and provide comfort energy. So we have these optimizers. We have these wonderful data loggers which are measuring conditions everywhere. They are measuring temperature, they are measuring outdoor conditions, they are measuring dew point, they are measuring dew point inside the space, and they are optimizing all of that to give you the best comfort, to give the energy savings, and to protect against condensation. So you can rest peacefully once you buy one of these systems. They're all available now, and the radiant cooling job will take care of itself. Just like a VRF system, as many of you might be doing, you know that they are so well designed for taking care of themselves. Radiant cooling also has gone far with the companies which practice them. And because it is all design, fit, buy, and install, you can buy all the components the way you like them and make your job more sophisticated. Otherwise, follow some more conventional system of not having that happen. So, for example, if it is a place where many people are going around and traveling and here and there and so on and so forth, you may not need such sophisticated system. So here is also one very nice system which I found with one of the companies which is doing radiant cooling, that they also provide this air treatment unit. It's nothing but a ventilation heat recovery unit which you get from other companies in India too. So it has a heat recovery wheel inside, it has a small cooling coil, it has its own little condensing unit which is allowing it to cool the air. It has a 6-row coil, and it provides just the right amount of air which you need. It also senses the amount of carbon dioxide with a sensor in the space and gives more fresh air or less fresh air. It senses the humidity, and so it provides cool air in case humidity is to be removed. And you can connect it to many other sensors to do all of that. So this is the partner of your radiant cooling system, the dedicated outdoor air system compact unit, right? So how do radiant panels perform? They are governed by this equation, Stephen Boltzmann. It's an equation of physics where the radiant cooling effect in BTUs per square foot or watts per square meter will be based on this calculation, 10 to the power of minus 8. It looks like a very small number, but it is multiplying the fourth power of the temperature difference. This AUST is the weighted average temperature of the room. It's about the same as the air temperature. So the difference between the panel mean temperature and the temperature of the room, and that's how the radiant panel performance is governed. Of course, the radiant panel performance is improved by colder water, it's improved by larger area. So here I'm coming towards the end of what I wanted to speak about. And so I will speak a little bit about that. So I came across this nice article, which is based on an ISHRAE chart, which I'll show you next. It's in the public domain, so it is not proprietary or it's nothing like that. So this person, this author, he wrote this article in this magazine, which is called Heating, Plumbing, Air Conditioning. It's a nice magazine. It's an online magazine. And so he wrote this about how to do detailed calculations. So because of the time constraint, and also that all of you must have this chart and we have to do a practical example and I have to show you how to use it. I am not going to teach you that today, but I am going to tell the organizers of this to share this reference with all of you. You can share my whole presentation. None of it is secret. All of it is in the public domain. And you will learn how to use this chart. So this chart is wonderful. So I'm just showing some parts of it. It allows you to decide the spacing between the pipes, whether they are buried in the floor, on the floor, or whether they are close to the ceiling. You can decide the spacing. So you can see over here. Here we are. Spacing. Spacing is here, spacing is there. And then on this side is the heating, cooling, what do you call it? the heat load per square foot. What is the flux of heat in that room? And then we have what is the entering water temperatures or entering hot air temperatures. So all these optimizations you can do based on what you know. So one thing you know is the heat load. So you know what is the flux. The other thing is you know the area which you have available to you. You cannot have more area than the floor or more area than the ceiling. That's all going to be fixed, right? Based on the architectural design. So your some areas are fixed, the heat load is fixed. Now all you have to do is to decide what cold water are you going to put inside, what is the density of the pipes which are going to fit in that space. Obviously, if you have less area, you have to put more density of pipes. And so this whole thing is a nomograph. A nomograph means you start somewhere, you go there, then you go there, and you read something else. You know, that's what a nomograph is. It's very interesting to use this. I will probably ask the technical group of ISHRAE to convert this to a software, which will be very nice. And I think we'll take the permission of ISHRAE to do that because this is in the public domain again, this nomograph. It is based on somebody's good work and good experiments, and even if you have to pay a royalty for that, some small amount, but that's a separate matter. But I think because we are good in India doing software, we can convert this whole thing to a very good software for designing pipe spacing for doing radiant cooling work. At this stage, I wish to tell you about Madhusudan Rao because he is not an HVAC engineer like some of you might be. He is more of a person on the solar front. That's his main business, I think, alternate renewable energy. He came into radiant cooling, which he thought is a very good idea to also save energy. And he learned all about it from wherever he learned. And so much of his experience is by practical performance and doing work and measuring surface temperatures, measuring flows, measuring pressure drops, measuring pumping pressure. So all this data and information he has gathered, which is why he and his people in that technical group are able to make a practical design guide, which is based on his experience and others' experience too. Jyotirmay Mathur also has done a lot of very interesting work. I visited, those of you who are in Jaipur or can go to Jaipur, you must visit MNIT's what do you call it? Radiant Cooling Laboratory. It's a nice place, and they have done a lot of experiment. Good. I brought this up. The boys over there, the young engineers and girls, boys and girls, they made their own radiant panel in the workshop using gypsum and using copper tubes. And I forgot to talk about this earlier, so I wish I had a photograph of it. So they designed their own radiant panels and they put them together. And I went to do a small ISHRAE training program there a couple of years ago. And so I spent time looking at that. And one other very interesting thing, since I want to tell you about radiant cooling, you know what they did over there? That you are wondering that chill water, producing chill water anyway is energy consuming. Yes, it is. So over there on the terrace, they put what is called an adsorption chiller. ADSORPTION, not AB, not B for Mumbai or B for Bombay, D for Delhi. Adsorption chillers are made in this world. They are made by one company in India also. They are very, very innovative. And they need the energy of hot water at 35 degrees centigrade. So it's warm water. So you can produce warm water so easily by using solar heaters, like you produce warm water to have a bath. And so that warm water, radiative water is coming, not radiative, sorry, solar heated water is coming into that 10-ton adsorption chiller on top of the terrace of that MNIT lab. And so they're getting free chilled water from the sun. And they also have put one heat pump. So on the days when the sun is not shining or in the night, the heat pump produces hot water instead and feeds this radiant cooling system. So the energy is so less for that 10-ton cooling lab which they made. Most of the time it runs free. And one of the rooms was where I did the teaching was radiant cooling on the ceiling, which I never noticed for a long time. So I was wondering where are the air conditioners. I couldn't see any of them. And long after I started teaching, that I came to know that this is a radiant cooling room. It also had windows, but it was very comfortable. And you won't have any fans running over there. So in some time, you forget about your comfort when your body doesn't complain, right? Comfort is a situation where psychologically you convince yourself that everything is fine. So actually, if you put a ceiling fan into a radiant cooling space, just the sight of the fan might psychologically make the people comfortable. They know they can switch on the fan when they feel uncomfortable. They may never switch off the fan, right? So this chart is continuing to tell you how to use this chart. The whole thing is very well given and explained, and you can learn all about how to use this chart from this thing. And maybe you want to do that as a practical experiment, and maybe we can teach this to a few people also if they are more interested, and we can have a good guide which will be, what shall we say? The design won't be empirical. It will be based on good scientific data and good experiment and a good chart. And so anybody who follows this and does this design is sure to succeed, right? So before I end, I wish to show you some pictures of illustrations of radiant cooling installations which are on the ceiling. I don't have many pictures of radiant cooling on the ground, which Madhukar can show you whenever he shows you. But it's very similar, and the work has to be done when people are not there, and it creates quite a mess because you have to cover it with cement. But once it's done, you don't even know that the pipes are there below because it is so nicely covered and structured. So you can see here these people are putting up the panels, and this is a case where it is not in terms of panels, but it's a whole slab is getting covered by pipes, and afterward gypsum board will be fitted up over there, and the whole ceiling will become cool because of the contact with the pipes. Here is a control system. So the zoning controllers are there. You can see all the pipes are coming here, and there are all sorts of valves to control all of this. And here is a manifold with all the pipes going at different places. The same picture will come again. And so when it is completed, you may not be able to see anything, just the nicely designed panels. And here is a wonderful gym. So this lady is practicing in the gym. It's silent, and the ceiling has got the radiant cooling over there, and it's wonderful. And because the occupancy is so small, one can reduce the flow of water through the pipes and make it comfortable just for her because she's all alone. And if more people come, then you can increase the flow, and all this can happen automatically, right? And without creating any sound, without creating any murmur, nothing at all. So this is a picture of what is there in that ceiling. These are acoustically designed radiant panels, so they even absorb some sound. And so you can see they're like a sandwich. And here are people installing, work in progress. The state of the art is quite advanced in India. A lot of people are doing this kind of work. It's taking time, but the contractors are making good money because the savings are good. And if you have a good customer, a good consultant, I think it's time we can move far ahead and tell the government of India, the Ministry of Environment, that we have pushed hard and we are doing so much of spaces of radiant cooling, and it will pay for itself in terms of the energy saved. So we must get somebody who will be able to help us with that energy saving upfront cost. So this organization, the Government Energy Efficiency Services Limited, EESL, now ISHRAE has a MOU with them. They are willing to take up this work and subcontract it to any contractor willing to take up such work. So I will be happy to connect DCI people who are interested with that EESL outfit, and we can look for work because EESL is connected with all government buildings, and so they can take up whichever building they feel like, and they can, I'm using a strong word now, they can bulldoze them into converting into radiant cooling, and one of you guys can go and do the work over there, and maybe the funding and financing will come from ESL in terms of saying they will take the assured savings, or the customer pays for it, because government organization will pay for it, and there will be huge amount of energy saved, and that can go into the record of that building saving, right? So I think it's a good future. And so I'm going to stop my sharing now so that we can answer any questions if there are any. As I told you, I'm not an expert, but I'll try and answer them. And if any of you over here, KD Singh and all my good friends, there are many people here I know and I wish to know more. KD Singh can also help me to answer the questions, or anybody can answer, because I am not the expert. I am just one of a person who learned something about this business. So before I ask any question, I just want to tell you about what I am doing with radiant cooling with three of my classmates whom I studied with many years ago. Those guys, other guys are not air conditioning people. One of them, we've got hold of a professor now in India where we will do the experiments. So we want to cool to a temperature well below dew point. So you will get condensation. But our radiant panel is very small. It's meant to cool a small room, such as in a rural area or in a small town or any even in a simple home. And that panel will have water or moisture which is dripping down, but it will be all self-contained. And there are lots of aesthetics which have gone into the design. We have patented it, which is why I'm able to talk to you about it, so that none of you guys get the bright idea. But whatever. So that will cool the room faster. The area is smaller. So the cooling, it depends on the delta T. So we are providing a higher delta T, but a smaller area to give the same effect. So there are many avenues that radiant cooling can find options to use, and even that kind of machine can be done with solar to cool it down faster, and so on and so forth. So let's look at some questions if there are any.
Yeah, thank you very much, sir. Should we take the question one by one that we have received? Q&A box, I'm looking that there are 14 questions and might be there
Oh
in the
boy.
chat box
Okay,
as
we'll
well.
try and answer them. Yeah, I can see them.
Okay.
Should I answer them that I can see them?
Yeah, definitely, sir. Please go ahead.
Tapas, because I can see them and I can answer
Yeah,
them one by one.
please go
So
ahead, sir. Please go
one of the attendees, what is done to avoid condensation? So to avoid condensation, the simple answer is the panel should never reach the dew point condition. So the dew point is constantly changing. So there's a dew point outside. So dew point can be easily found out from the psychrometric chart. There are also dew point sensors. They will sense the dew point of air outside, but more important to sense the dew point of the air inside. So when you're reaching closer to the dew point, then that panel has to have less water flow, so it will never reach the dew point. Most of the times, this is never a problem because the dew point inside is so much lower than the panel temperature. So the good thing about radiant cooling is that we don't have very cold panels. We have panels which are quite higher than the dew point temperature. We are not removing moisture by the panels. We are removing moisture by DOS. So you're not never going to get this condition. This condition sometimes comes in what are called chill beams, but I'm not going to talk about that here. But in radiant cooling, that is not going to happen. How to compare radiant heating or cooling to tons of refrigerant? Okay, so that's very simple. So let's talk about cooling. So first of all, when you are doing the cooling load, you do the cooling load sensible heat separately and latent heat separately. As you do the cooling load calculation for a hotel room, because in the hotel room, that fan coil unit is not taking care of the latent heat. That is done by a treated fresh air system separately. So you calculate the sensible load of that room, and that is going to be BTUs per hour. Now you consider and convert that to BTUs per hour per square foot of some surface. And so that is the way you will be designing your radiant cooling system, for which we have to have a separate class. I showed you that nomograph. If you study that nomograph, you will come to know that from the sensible load, how will we convert that to a radiant cooling design. Share my presentation. Yes, Rajiv Kumar from Voltas, you will certainly get it. I see your number over here. And my email ID is vikrammur@gmail.com. If you don't receive it from the organizers, you're welcome to ask me. But I'm sure the organizers will share it with all of you because it's a generic kind of presentation, right? It is not of a company. It's not of a unique technology. This technology is in the public domain. The only unique thing about radiant cooling is better and better systems of control, better and better systems of piping, and so on and so forth. Okay, Shankar Gime wants the PowerPoint. Since I know Shankar Gime, he will get it. What's the difference between air temperature and radiant temperature? Okay, so that is answered by me in one of the slides. Please look at that slide carefully. So there's something called a mean radiant temperature, which is the product of all the surfaces area into the temperature of that surface. You sum up the whole thing, the sigma, and you divide all of that with the sum of all the areas, you will get the mean radiant temperature. And then there's an air temperature in the room, which you can easily measure by a thermometer wherever you go. The temperature in the room may change your thermometer very marginally. Unless you have an accurate thermometer, you may not detect any changes of temperature within a room. And then there's an operative temperature, which also I showed you is the average of the air temperature and the mean radiant temperature. So that is the operative temperature, which is the third form of temperature. Okay. So now I don't see, oh, there are more questions. What is the limitation on heat removal for radiant system? Yes, radiant systems can only remove sensible heat. That is their limitation. I don't think there's any other limitation. They cannot remove latent heat because you don't bring the temperature down below the dew point, which is required to remove latent heat. For that, you have a dedicated outdoor air system. I hope that answers your question. If not, I will request Tapas to allow people to talk if they want to. Issue on acoustics, of course, it is very nice. There is no sound, there is no fan. Therefore, acoustically, the place is wonderful. If you have an architect who's more particular about acoustics, then tell that architect to get an acoustic engineer and design surfaces which absorb sound if there is going to be sound over there. And what else is there? So the embedded pipes and flows is a very good idea. It's the best way. I would say it's the best way to do radiant cooling because you know why it's the best way. I didn't cover this topic, so it's a good opportunity for me to talk about it now. Because you are sitting on the ground or on your chair, you are closer to the ground than you are to the ceiling. Most of you are not more than, in fact, all of us are the same height. Once we sit on a chair, there's not much difference between our heights because our torsos are approximately the same size for a tall man and a normal man. So the cooling will come very quickly to you. Your body will lose the heat to the floor below faster than it will lose its heat to the ceiling, which is cold above. So that's why I think the floor radiant cooling from the floor is going to be far more effective, right? Then the question is, where will we get where will get QI of all type? Okay. I think this is going to talk about the flux of the various types of surfaces. I don't know the meaning of this question, so you please allow this person to unmute what he's saying and share the presentation.
I
Yes.
request.
No need a PDF. You're most welcome to take it in PowerPoint and do what you want with it, but don't, you know, you keep it correct. So if you want it in PDF, you're most welcome. Is the same system a chill beam system? This is a very nice question. In answer to your question, yes, the chill beam system is similar, but it's not the same because the chill beam system, there are two types of chill beams. One is a passive chill beam in which there is no fan, but the chill beam works on the principle of convection where air is set in motion and wherever the chill beam is mounted above, the air from below flows above because the beam is cooler. But some chill beams have air flowing through them. There's a pipe in that chill beam, like a tube, and that air is blown, which is probably treated fresh air, and that induces air to go faster to that chill beam. So the chill beam is a far more sophisticated technological product than radiant cooling because radiant cooling is all about passive cooling only by radiation, whereas chill beam have a combination of radiation as well as convection. So the chill beam might work faster. Okay, but the chill beam, you'll have to have many more chill beams to give the same level of comfort to all the people compared to a radiant cooling. Where is your technical class on radiant cooling heating? Last time I missed. So first of all, I am not a regular classroom teacher, though I wish I could be that. But we can have a class for teaching you more, whoever you are, because these guys' names don't come, anonymous attendee. So any specific info available on manufacturer rating? Yes, there is. But since this is a program of ISHRAE, I cannot start giving you the names of these fellows who make panels here. But a good Google search will get you the name of radiant cooling panels of people in India, and many of them are making now. There are some great manufacturers. One of the persons who retired from Infosys, without mentioning his name, he has started a big business of making these radiant cooling panels, and I believe he's doing very well selling those radiant cooling panels. But here's my advice to you. I would advise most of you who want to do a radiant cooling job, do it on the floor. Forget about all these panels and this and that and the other. It is, you can get a good civil contractor, a guy who does flooring and good quality mason. You get him and you do the whole work on the floor with the flex pipes. It'll be a far cheaper cost of doing the things, and only thing your client is to give you the free time and space of that floor to be able to do your work. In 3 days time you can finish the whole work. So I think you can pack him off for 3 days for a holiday, your client, and you can do the work. Is radiant cooling suitable for the Middle East? Of course, it's suitable for the Middle East. It's suitable for which is hot and dry climate, extremely suitable. But I'll tell you, here is the point about Middle East or anywhere else. When the temperatures are very, very high outside, right, then cooling for a human being psychologically is far better to do it by convection than by radiant cooling, unless we are able to prevent the heat ingress into that space in the Middle East. 52 degrees temperature outside, 50 degrees temperature outside. Some parts of India also are reaching 50 degrees because of global warming. So then your walls will bring in so much of heat, the radiant cooling will be doing all its work to cool that wall instead of cooling the people over there. So in such spaces, we must take care of the walls not giving in heat. But the simple answer is, because we are all getting more clever about design and working with architects, we must bring in less heat into a building by natural process, by passive method. And then the heat load becomes very less, and then radiant cooling will work anywhere, except where you violate the dew point condition. What are challenges to use resident cooling? Okay, so resident cooling is becoming the hottest big subject for radiant cooling because people love it. If you get a client who has a big flat in Gurgaon, in Aralia's building in Gurgaon, which is 4,000 square feet houses and all that, you tell him, let's do radiant cooling in your house. In fact, anyway, I have a friend who lives in one of those buildings in Delhi, and I told him about doing radiant cooling, except that his house is already air conditioned long back. So it is a big task for him to get all this thing done all over again. But it's if a new house, then we can put the pipes in the whole flooring. We can have a small chiller. Of course, because it's a big flat, it will have some kind of balcony where you can put the chiller and do it. So I think the good way, the answer to Anshul Gautam's question is that you have to work in the beginning with the architect and the contractor and the developer to do this. And I'm sure that guy will be able to sell his flats for 10,000 rupees a square foot, much more than that, higher or whatever, because you have done a unique job where he's not going to have much problems of maintenance. There is not going to be any sound. He will be a master of his own cooling, and it'd be wonderful. I think it's a great idea. Radiant cooling is the future. How does absorption cooling work? Okay, okay. So, yeah, so this is a good question, but this is not a class for that. But so you put in absorption cooling in Google and meet Saya. You put in the chat your email ID, and I will send you that information which you want. And it works very well. It works on the principle of migration of doing cooling by vacuum and by using desiccants. So that's how it works very well. And it only requires lukewarm water temperature. It's a wonderful invention. It costs a little more. It may be costing twice as much as a normal chiller, but the cost will come down as more and more people buy it, right? And right now, the more major customers are those who have waste heat. But the moment we couple it with solar, then it's a win-win situation. So Milind Sardesai, my good friend from Goa, is asking a question. How radiant panels compare with chill beams? Yes, they do compare well, because I think Milind Sardesai is in Goa, and one of the hotels which he was involved in. Hotels, they've used chill beams in the rooms, which Milind told me about, which is quite unique, a hotel room with chill beams. So they do compare quite a lot with that. But over there, just as somebody asked a question, we have to be very careful about dew point. We should not allow the lovely air of Goa to enter those rooms, and the chill beam temperature is lower than the dew point. Then condensation will take place. The same thing will happen with radiant panels. But radiant panels doing in individual rooms is not a great idea, because you have to do each room separately. So it is much nicer done over larger areas, 2,000 square feet, 3,000 square feet. Then you can do 3,000 square feet at a time, whereas hotel rooms would be some 200 square feet. So unless you combine the whole floor of one whole floor with a common piping, but then we can't control each room separately, right? Unless we have those manifolds for each room. I'm sure it can be done, but I suppose for doing that for a hotel, Milind, it would take a lot of planning for execution to do it, where the chill beam is much easier to bring it in and connect it to some chill water piping like you connect a fan coil unit. So that is my answer to the question. Although I think Milind and I can come on the phone and we can talk about it sometime. Can we get 25 degrees centigrade reading? Yes, of course you can get. So this answer to Anshul is, I don't know what Anshul is referring to as 25 degrees centigrade. If he is referring to as 25 degrees centigrade as the perceived temperature in the room by an occupant, of course you can get. You can get it even lower based on the dew point being lower. So most times radiant cooling, everybody feels 24 degrees centigrade. That's my answer to you. Josie Rivera. Leaks on embedded tube lead to, yeah. So this should never happen, Josie. You should never get leaks on embedded tubes. Just like we do refrigerant piping for VRF. We don't get leaks. Good projects don't get leaks. Ask KD Singh. He's not going to have any leak on his job, otherwise his reputation is at stake. Right? So you also cannot afford to have embedded pipes leaking into the ground. So we have to be very careful about testing. So testing is very important. If you spend 4 more days doing testing and pressure testing and checking for all the leaks and stages, this will never happen because it's all going to be buried, especially if it's in the floor. If it's in the ceiling, no problem. You have to remove that one panel and replace it, right? So the ceiling offers you that protection of a leak, whereas the floor, you'll have to dig up the whole floor. But most likely that will never be the question. Disadvantage of radiant cooling system, this is a long story. The disadvantages, if I have to talk about it, is that so actually there are no disadvantages. There are only advantages. But this is a good question. The disadvantages are that it cannot be used in places where humidity is high, where the sensible load is lower than 70% of the total load, then it cannot be used over there. So that's a disadvantage. Share the presentation. Yes, Suresh, you will be share the presentation. What will be the RH? How to control RH? RH is fully controlled by something else. RH is not controlled by the radiant cooling system that only takes care of sensible heat. So radiant cooling is nothing to do with controlling RH. You control that completely with a dedicated outdoor air system. Like a treated fresh air system, you can increase the amount of cold air in circulation. You can lower the temperature of cold air which is coming in. That's how you will control the RH very well. And it's very easy to control because your air quantity is very small and you can easily modify the treated fresh air unit to measure RH and blow in more cold air, less cold air, lower temperature, higher temperature. And so RH will be very well controlled. In fact, RH control is so well done because of it, you have separated the sensible from the latent. Though dripping condition does not happen, but moist surface can cause, yes, of course. If your surface becomes moist, these biological things can happen. So this is a question you should ask Mr. Madhukar Rao when he comes on your program, or even if he doesn't come, you can answer it yourself. Why is it happening in the first place? Why is that surface become moist? Because it reached close to dew point. That's the answer. So you must be able to have, it's very easy to know the dew point. If you have a wet and dry bulb thermometer in the room, or if you have a wet and dry bulb, what do you call it, digital temperature sensor, then you can easily make a program. There are many softwares available which take the input of the wet bulb and the dry bulb and will give you the dew point as an output. And so that output, because it can be given as an output, that is your dew point reading, which can raise alarm. So when the dew point, and you compare that with the surface temperature of your floor, if the delta T is less than a certain amount, you have to switch off the water to that floor. It has to go off, and no longer that will happen about that. But if it does happen, if it's on the floor, you are supposed, okay. Here's the story. I want to tell you a little joke. Do I have time to tell a joke, Tapas?
Yeah, please.
Joke means a funny
Please
story.
go ahead. Please go ahead. Yeah.
Hello.
Yeah. That's
Sir,
because
it's your show. It's your show.
No, because of time. I've taken a lot of your time. That's why. So my partner in Bombay, he once sold what do you call it? A fan, which high velocity, low speed fan, HVLS fan of smaller size to one ashram, in Bombay, where the priest is coming and giving his lectures in the evening on a lovely marble floor, smooth marble floor. And in Mumbai is not a great place to give evaporative cooling kind of solutions of this fan. And so that fan also blows a small mist of air, misting, so that it can give a sort of sense of cooling. So that's what happened. He put these fans in that building, in that ashram auditorium, and ran the fan. And one fine day, the priest walked in over there, and he went sliding from one end of the room to the other, and he almost broke all his bones. So we almost had a police case on us for selling that fan. So that's the funny story. So the same thing I want to tell you. The moment there is something slippery on the floor, you will slip, or the lady of the house or somebody who's smarter than me will notice the floor is getting moist. So you will start mopping the floor. You will not allow that floor moist to collect dampness and to collect mold. That will never happen because you can see the floor. The ceiling is much higher above you, but if it's going to be on the floor, you will see it. But in answer to your question, if that moistness is happening on the ceiling, it's not a good thing. That means your system doesn't have the proper controls in place to prevent that from happening. But now, radiant cooling has been in practice in India for 15, 20 years. A lot of these things don't happen at all because of the development of the technology. Similar radiant cooling, yes, wonderful. Okay, so radiant cooling, this is a good question if I understand it. So if you go to a supermarket and you stand in front of those open freezers where there is butter and milk and all these type of things are kept on trays, and that whole open fridge is quite cold. If you go and stand in front of it, you will feel really nice because your body will lose heat very fast. If you open the refrigerator door of your house fridge, if it's a nice big tall fridge, you will feel very cool because your body is rapidly losing its heat to the refrigerator, which is colder inside. Radiant cooling is exactly that, except the fridge is a very small radiant cooling surface, and the radiant cooling which you do is much bigger. And a deep freezer, if you open a deep freezer, you will feel cooler even faster. Specification of pipes, yes, these are plex pipes. If you read the word PLEX pipes for radiant cooling, you will get all sorts of supplies for them. They are mostly made of a plastic, which is very good conducting plastic, and they are flexible, so you don't need to put many bends. You can turn them around, make a U bend, and all sorts of things you can do, and you get all the fittings. So I don't know what is the Rahul Dub is answering this question. It would be great to understand your patented radiant pan. Okay. Rajneesh, we'll talk to Rajneesh separately about what I'm doing. Yes, we will. Maybe we'll ask Rajneesh to make what we are patenting. Cooling pipes, Subhash Doshi, with pipes. Arrangement of pipes. Okay. This arrangement is going to be made clear to you in that attachment which I gave, or rather the reference about the design of how to space the pipes. That nomograph of ISHRAE will show you all that. What is fouling? Good, good, good. I think it's a wonderful question about the fouling effect of pipes. Suppose we have water which fouls the pipes inside because of scaling, we are going to be in deep trouble. So, because it's a closed system, and everything is not going to be having fresh water coming inside, this fouling is not going to take place. Also, you know now that it is very easy to clean a system if ever you wanted to do, because it's connected to the chiller. You can have some place where you can open it, you can drain the water, you can pump in anti-fouling chemical into it, and it will clean the whole thing out, which is what we do with chillers also when they get fouled. So fouling will be easily rectified. Nowadays, everybody is using plate heat exchangers which have such small tubes, and fouling is a problem for them as well. But because of modern methods of preventing fouling or removing fouling if it happens, but the best way to do it is to give good water in the beginning, and never to have your problem. Limitations. I think I should stop now because so many questions are here. I'm very new. Okay, Mr. Arnab, you will get the response time is a limitation. Yes, immediate cooling. So where in the world, Shaurya Singh, where in the world in central air conditioning and comfort air conditioning do you want the cooling to happen the moment you come inside the room? It's very rare, right? And if you want that, then radiant cooling is not for you. You have to have some blast freezer which blows cold air on your face, and so you feel very cool. So the best quick way of cooling is a car air conditioner, because when you put on your car, start the engine, put on the air conditioner, and the blast of cold air comes out of the blowers of your car, you're sitting so close to it, you feel cool so quickly because your face gets cold. Here's what I want to tell you, Shaurya. The human body feels coldness very quick if you can cool the head and neck. So that will not happen with radiant cooling. And even central air conditioning in a large office, wherever the air is coming from, the room doesn't get cooled fast. Most commercial buildings start the cooling 1 hour before the people come in. At home, also, if you come into a warm home from outside and you put on your split air conditioner, it's going to take some time. But if you stand under that split air conditioner with the air blowing on your head, you will feel cooler faster. So we as human beings have to become adapted to that. Cooling is not going to happen instantly. And where it's required for a industrial process, then obviously radiant cooling is not the answer. Mr. Pramod, I will request Tapas to please copy this email ID of Pramod, and anyway, he's going to share it with everybody. What is the main source to keep cool water? I don't understand the meaning of this question, but you can have storage. You can have water stored in a storage place. You can add ice to it to keep it colder, but then radiant cooling doesn't require such cold water. Calculation, yes, the calculations are there, and we will have to have a separate class for calculation. But early calculation you can do by studying that graph which I gave you. What is the panel output temperature? We supply 18 degrees. Okay, good. So if you supply 18 degrees water into that, you should supply it. Then you can expect the panel to become 22, 23, like that. So the thing about radiant cooling is soon everything becomes the same temperature as that panel. It's not like air conditioning where you supply air at 12 degrees and 14 degrees and then the room becomes 23. In radiant cooling, whatever the panel temperature is, the room will become very close to that. So if it's at 18, the delta T for the room will hardly be 3, 4 degrees, like that. Okay, so that's why radiant cooling is very even, and we are not worried about the latent part because that is taken care by a separate system. Minimum sensibility factor, I would say 0.8. 0.8 is a good thing. If you are going to get to zero point 0.7 and all, then radiant cooling, you have to think about it and you have to separate these two loads. But mostly, radiant cooling is going to be for standard comfort air conditioning jobs. It's not a good idea to use carpets for floor cooling because they will become an insulator of the coolness which is coming out of that floor. So I want to tell you about carpets. Carpets are not good for Indian climate because they collect dust, they collect humidity, they will become moist after some time. Mumbai airport was fully carpeted, so was Delhi airport, and they removed all the carpet some time back because of the same problem of dust and dirt, I think. Of course, it's not radiant cooling, but airports would be a wonderful place to do radiant cooling. I think, it would save a lot of energy. But airports have another system of cooling, which is called displacement ventilation, where we are blowing air at lower heights, not at very tall heights. And of course, airports have such huge diversities in the cooling. So radiant cooling may not be the right answer. So I correct myself. Radiant cooling is not applied in refrigeration. No, because it is higher temperature. In warehouse and recycle center, yes, you can use in the warehouse depending on what that is. But if the warehouse is requiring lower temperatures, it won't be possible. Most of the applications in radiant cooling are simple comfort air conditioning, which is 90% of the business of air conditioning is comfort air conditioning, right? So India, just for you, I'm just closing this thing over here. India's largest uh, contribution to air conditioning is the residential sector. 70% of all air conditioning in India, which is about 10 million tons of air conditioning per annum, is residential. Right. So if we want to get good business in India, we have to look at the residential sector, whether it's VRF, whether it is radiant cooling, whatever it is. All of us, or district cooling is another good application for residences. And there's a wonderful person in Hyderabad. You should call him for I'll come with him together about district cooling for the residential buildings. So Hyderabad has many district cooled residential buildings. Maybe I should ask that person, why don't you get into doing radiant cooling for residential buildings? So I'll stop over here, Tapas, because I've spoken enough now.
I think
By now, half the guys must have gone away.
you
Anyway,
have
yeah.
answered all these questions, I believe, sir, and in a very quite good manner. And definitely, I think we have to make more workshop on that and lots of questions coming. So we request you to again think about this topic and what could be the extension of this topic. We'll have to
Certainly. Yeah, I'll help you. I'll also get for you, Mr. Madhukar, Madhusudan, sorry. He's a good person to continue from where I left.
So before going to end of this session, I will just a few minutes to share something. This is the HVAC conclave that Delhi chapter is going to organize on 28th of August, Saturday. And this will be one kind of platform where corporates will be there. We are targeting 20 corporates over there that will be on the virtual platform. And attendees can interact over there. Video will be shared by corporates or companies. They can interact directly. There will be meeting room and all kind of facilities will be there for the attendees. And few information is already shared in the chat box. For other information, you can contact me directly. My number is given over there. So it's a one of its kinds event and first time we are doing. So we need your support for this. And that is again I'm recalling this. That is on 28th of August, Saturday, 10 to 6 will be the time. So moving forward again, as a it's a request for everybody. One who is non-member over here, we request you to join ISHRAE. And this is the only motivation we get from your side. Members is our strength, and definitely I have shared the link as well. And you will have to just click on chapters, and you will have to select Delhi chapter. After information filling form, you will redirect to the payment page, and very easy process to get enrolled with the ISHRAE. There is no any complexity over there. And there are pennies of amount that will have to put over there, and you will be the member. And everybody knows that I think ISHRAE doesn't need any introduction over there. This is a large platform of HVAC and our industry. There is no any such platform who can compete with ISHRAE, what I believe. And again, we request you to join. And this is the thing we get motivation from your side. For any suggestion, any improvement or anything, you can share your views, your suggestion, your points in Delhi chapter 1981@gmail.com, or you can send me directly at executive.secretary@dcsra.org. So not getting much of time, I request further President of the Delhi chapter of ISHRAE, Mr. KD Singh, to execute vote of thanks. Please,
Good evening.
sir, over to you, sir. Thank you.
Yeah, good evening, everybody, and good evening, Vikram, and thank you very much for this wonderful presentation. And I can only say that I enjoyed every minute of the presentation that you made. And I would say that such a topic which seems like very complicated has been explained to you, has been explained by you, and answered so well, so simply by you that it seems like everybody can do it. So thank you very much. And from on behalf of the Delhi chapter of ISHRAE, all its members, all the attendees who have been here on this program, a big thank you to you for the wonderful session and the wonderful knowledge sharing session that was there today. I think anybody who came in on the session today has gone back, richer in terms of knowledge. It's been worth the time that one's invested here. So, and I've always seen you. I think you're one of the most polished and a very good leader, I would say. Even as a president of the national president of the ISHRAE, I think you did a lot of wonderful work. So thank you, Vikram. I'm really indebted to you for having spared time, and we look forward to more of your programs so that our members from the Delhi chapter of ISHRAE and others can benefit from the wealth of knowledge that you have. So I would, I would end the session by saying thank you very much for being here today. We really enjoyed every minute, and we look forward to more sessions with you like this. I think you spoke of number of topics, number of things that you covered, including you spoke of the structural cooling, the residential area. So I think another very good area which I think becomes a breadwinner for many of us would be just to structurally cool that building using cooling tower water. I think Madhusudan is the right person, as you rightly said. Madhusudan Rao is an expert at this, and I think that will open a lot of doors for many of us, in terms of achieving energy efficiency and addressing the residential sector. So thank you, Vikram. Thank you very much for this wonderful session.
My pleasure, KD. Anytime for your chapter.
Yeah, we look forward. We are privileged and honored to have you, and we look forward to more of your sessions, as we go along this ISHRAE society here. So we look forward to that, and hoping that the pandemic times are over. So we look forward to seeing you sometime, in Delhi. So that.
Oh yes, it's my second home, KD. I'll be there soon.
Yeah, okay. Sure. We really look forward.
Yeah. Okay.
Yeah, so thank you all the sponsors at the DCI for having helped us to keep the society going, and Tapas ji and the entire admin staff who's put this together, and each one of the attendees who found time to be here today. So thank you each one of you, and thank you everybody. Thank you Vikram. Thank you very much once again.
Thank you, sir. Thank you, everybody. Thank you very much, sir. So, with your permission, I'm closing this session, sir.
Yeah, sure, Tapas ji. We can end this session. Thank you.